Hello and welcome to aspConf. This is Chandar Dhal and today we'll talk about what is search and why search is important, both for the enterprise as well as other applications. We will as well talk about the different components of search. Then we'll introduce Lucene, which is more like a powerful search utility in a DLL. And this will be followed by a real-world demonstration of search. That's my email and that's my Twitter. However, if you search for me on Google, you should be able to get to me. We shall be going through why search is important, and by that I mean both internet and enterprise search. We'll take a high-level overview of the different components of a search solution. Lucene is the best it gets to finding the low-level search solution on the open source platform. We'll start with the core concepts to understanding Lucene better, which will be followed by a demo. And then we'll talk about the best practices and anything relevant. Here are some interesting facts. The one that's really more interesting to me is the second one. The moment Google introduced the Did You Mean feature, it almost doubled the searches. What that tells us is that as human beings, we like UX. User experience is more important to us. So no matter what the algorithm is behind the scenes, the searches doubled the moment we added one feature like that. So how important it is for us to understand that whatever is going on right now in the search industry needs to be introduced into our application too. So why search? It's very important to understand why search is important. Data versus value creation. Creation of data is just a small piece in the bigger scheme of things. Being able to get to the right information when you want it is the key to making enterprise efficient. Anywhere from emails, documents, transactions, intranets, which are more likely to be the internal sources of information, to websites, social media, etc., which are the external sources of information. Search is that one key piece that brings value to an organization. Raw data is important, but it's more important to be able to make sense out of that data and finally be able to make informed decisions. There are a few very different formats in which data could be received, and that's text, audio, and video, including visualizations like pictures. Whereas text is something that seems to be simpler to deal with, as of now, most of the searches for videos and audio are also contingent on the quality of textual metadata associated with it. It's very important to understand why search is important. Creation of data is just a small piece in the bigger scheme of things. Being able to get to the right information when you want it is the key to making enterprise efficient. Anywhere from emails, documents, transactions, intranets, which are more likely to be the internal sources of information, to websites, social media, etc., which are the external sources of information. Search is that one key piece that brings value to an organization. Raw data is important, but it's important to be able to make sense out of that data and finally be able to make informed decisions. There are very few formats in which data could be received, and that's text, audio, and video, including visualizations like pictures. Whereas text is something that seems to be simpler to deal with, as of now, most of the searches for videos and audio are also contingent on the quality of textual metadata associated with it. User experience. Search is costly. Sophisticated systems are costly. But again, a trade-off needs to be made into how much effort needs to go into creating a sophisticated system. That kind of an argument is acceptable internally in your organization. But if your company depends heavily on the user experience provided to the client, search may be more a necessity than something good to have. Imagine your search box without an autocomplete. Imagine a search without spell check. With Google setting up a high benchmark for search in general, we as enterprise developers need to create a similar experience for our customers so that they are not disappointed. Is it hard? Not really. We don't have that much data to search from, and since we know our limited data well, we may be able to create a better search experience that might be less redundant. This is a great picture that explains why user experience is really important for your business. I'm sure all of you have used Amazon, eBay, or any other online shopping website. Now, what is it about those results that are appealing to you? First of all, you need the results to be highly relevant to what you're searching. If you're searching for a cell phone, you really want it to be that particular cell phone model. Let's say you have a sale going on for a particular monitor. You would want that monitor to show up high in search rankings compared to other monitors. Third is obviously performance. If the customers find your website performing relatively slowly, there are less chances of the customer shopping at your website. When it comes to search, precision versus recall needs to be understood. Precision is the fraction of retrieved instances that are relevant, whereas recall is the fraction of relevant instances that are retrieved. Let's say I made a query on a company name, which is RIA Consulting LLC. If I look at my data store, the total results that are in my data store are 120,025. And if I look at the relevant results, I only have 25 relevant results for RIA Consulting LLC, and rest of it is irrelevant results. So when I made the query, the results that got retrieved back were just 15. So that makes my recall 15 by 25 because I know that there were 25 relevant results, but my search only gave me 15 results. Well, so the recall is 15 by 25. But at the same time, out of those 15, only 15 were relevant to my search. So I did get 15 results back. Out of 120,025 results, I get back 15 results. That's a little complicated because I did get 15 results back, but only 12 of them had the search string, which was RIA Consulting LLC. So what's my precision? It's the relevant results I got retrieved divided by the total results that were retrieved. So it's 12 by 15, which is not really bad. It's really good when it comes to real world search applications. Now, and that's where I say that when you know your data well and your data is less than what Google is searching against, your precision could actually be much better than what their precision is. Because let's say you're Best Buy and you're making a search on monitors, you really know what are the monitors you have. You make the same search on Google, that might be a search against so many different pages. In layman's terms, an index would be a format that is easily searchable. It does make sense to have indexes. Think of an example where we have 20 gigabytes worth of data. You don't want to be searching all your 20 gigabytes to get you something that you can get very easily. But if you index your data, you may have just 10 megabytes of indexes that you need to search from. And it's probably a smarter decision if you really know that those things are going to be searched a lot more often than others. Searching is important too. It could be the same exact data, same exact indexes, but the way you search it and how you put the algorithms on top of it makes your searching faster. Analysis. The text we have needs to be broken into tokens. What determines the size of these tokens? Is it supposed to be one token per word? If yes, then what about compound words? Would you like to create a single token out of a commonly used phrase? Passed away and passed out mean two different things, but if there is a sentence like, he went off his house when he heard the news about someone who passed away, if passed away was not a single token, this sentence would appear in both the searches. So Lucene has quite a few different analyzers built into it and also lets us extend and create our own analyzers. And the fourth and the most important one is performance. Whatever we do, we can add up a lot of overhead, and we don't want to do that. So what is Lucene? A lot of people call it as a Google or Bing in a DLL because all it is a library. It's a C# library. Well, Definitely, it was not started in C Sharp. So if you look at the open source specs, it's actually, I think it was actually started in Java. So it's a free open source library. It's been ported into C Sharp. It's document based database. It's schemaless. It's based on the concept of an inverted index, which we'll look into it in a second. It's pretty extensible and highly scalable. As long as you can scale .NET, you can scale Lucene.NET too. Who uses Lucene? There are a lot of big companies that use Lucene and also some startups. So there are some familiar names right there. Let's take an overview of a search application. So let's say we have a document. Now, a document really doesn't mean a document. What a document really means is a unit that you can work with. In this case, my document, all it takes is a name, company, and my skills. And then it uses an index writer. What does an index writer mean? Index writer is a Lucene.NET class that actually writes to the that makes you create an index. So the index writer, after using an analyzer, and there are different kind of analyzers we can talk about later, tokenizes the input and adds to the index. So let's say I had this document and my analyzer would go ahead and remove certain things, which is really not much to remove over there because it's a very concise document. But let's say it was a big document with paragraphs about me, it might take the title and it might take the whole body and not really put everything in the index, but just store part of it and take some tokens from there that help retrieval easier. Let's say there are white spaces, it can remove the white spaces. It can remove redundant words like a, an, and the, and then create my index. And it writes the index. So once the index is written, we can query on that index. So if we look on the other side, which is a query, and all I query about is skills Hadoop, and I want to query for that. Once I have the query, it's going to the index searcher, and using the same exact analyzer which I used in order to create that index, once I have that, my index searcher, which is another class, and I use that object to retrieve the data, gives me the hits, which is all the documents that got retrieved after putting in this query. And then I can get to what I want to from those documents, from the list of those documents. And that's how simple it is. So the first process was creating those indexes, which could be done one time, and then you can keep retrieving unless you want to go change your index, which could be done in near real time. Now it's time for the demo. This is probably the longest hello world you've ever seen in your life. Well, part of the reason is that we're going to be doing both. We're going to be writing to the index and also reading from the index. You'll probably see a lot of statics in the code, which is okay because I'm assuming that you're going to be using IOC or something else in a web application. Using static is probably not the best thing. But for the demo purposes, we're going to go ahead and do that. The first thing I'm using is a directory, and second is an an analyzer. And the third is going to be an index writer. Now keep in mind, I'm referencing Lucene here. That's why I do get all these references. So Lucene.NET, you can go to NuGet and get it. Otherwise, whatever version of Lucene.NET you want to add as a reference, you can do that. So index writer, and I'm just going to call it writer. Now it's a directory. Where my indexes are going to be stored is going to be the directory. In our case, to make things simple, I'm going to just go ahead and create a RAM directory. Now a RAM directory really means that it's going to create indexes in virtual files inside the RAM. Then I'm going to go ahead and use a simple analyzer. There are a lot of different analyzers you can use, but for now we're just using a simple analyzer, which is going to break all the data into tokens. Well, in order to write, I need a writer. And to write to the index writer, I'm using an index writer class. I'm going to pass in the directory, the analyzer, and index writer.maxFieldLength. As of now, it really doesn't matter because we have limited data, so we're gonna just use limited max field length. The next thing would be to write a document. Now, what's a document really? A document in this case really means some kind of data that you want to add into a document. You know, sometimes think of your email being a document, or let's just say the communication you receive from someone being another document, an employee's data being another document. So document really depends on what you want to create a document as. Now it could be 3 different entities and you could have one document for that. Now since it's schemaless, you can add whatever you want to. So when I go and create this function, it might be easier to see as a full screen. I'll have to go and create a document. Now this is a Lucene document, by the way. The next thing I'm going to do is document.add and add some data in it. A document contains fields. Now different kinds of fields. Field is more concise form of data. So something like, say, okay, abstract, title, or whatever you want to call it. I'm just calling it text to make it simple. Now it's saying, do you want to store the field? Now, yes, it does make sense if I have something like an ID. I want to store the ID field. But if I have something like a big body of HTML body of a web page, I may not want to store that field because that's going to take a lot of space. But in this case, it doesn't matter because all we have is just one string and we're going to keep it simple. And that string actually is nothing but my name. So it's very small. So it doesn't matter if we store it or we don't. So once we've written the document, the next thing we need to do is commit the writer and actually close the writer. What's the next thing? I want to be able to search it. So in order to search it, maybe I want to pass, I want to return a JSON result and search this text. So when I search this text, I need a reader. So in order to read from this database, from the index, I need a reader and a searcher. Now what's a reader? Think of reader as a data reader object, which really opens up the connection and then you can read the data from it. And all the searcher does is really takes in the data reader object, the index reader object, and then it searches on it. So in this case, we will have index reader dot open. Now it's the file info path, and there are 14 different overloads. In this case, we're just going to pass in the directory. Now that's why I had it static, so that I can reuse the same exact directory which I had. But obviously not the best thing to do in web apps. So I have searcher, and then I go index searcher, and I'm going to pass in the reader. And then I'll have to return some kind of JSON result. And maybe in this case, I might want to create a class that has this data, or I can actually just create a function here that gets me all what I need. So when I need to search, what is it that I need? I definitely need the searcher. I need the same exact analyzer that I used to create or write to that index. And then obviously I need the text, whatever I'm searching on. So if I use Visual Studio to create a function for me, I'm inside the index searcher method. Now here are a few things. One is, as you see this is text, and this is more like a string. You may not want to do this. You may want to create a config file that actually has this value of these different fields, and you can use them later. Otherwise, you can get into all sorts of string errors. So let's just do that. Call it string, because when I search it, I need the same exact field. The other important thing is that for some reasons we need to work with the different Lucene versions we have. Now you can find it in lucene.net.util.version and then Lucene version. Now you can see there are different kinds of versions right here. And you can see it's somewhere between Lucene 2.0 to 2.9. And probably the best one is just using lucene.current. Now this is kind of neat because lucene.net has different versions, and how do you really know what version you were working with? And if you do spread that code all around, then you don't have one single place to change it. So I would again suggest that this can go in a config file. All right, so we're good to go, and we can write the search function. What do we want to return? You know, we need some kind of result object. And to make things simple, never do this in your controller, but for now I'm going to do this. I'm going to create another class right here, which I'm going to call result. So if I have public string results, it could be another property. And maybe I want to give another property, which will just be a list of string. Well, to make things simple, usually I don't use this kind of naming convention, but I will, because it's again a hello world. So hang on a bit. I promise that it's going to be the longest ever hello world application. In case of searching, what do we need? First thing we need is the query, and then we also need to parse the query. So if I have a query parser, make sure you do not use the remotion link parsing query parser, and you use the lucene.net query parser. What does it need? It needs a Lucene version, which we already have. It needs a field name, which we do. And then the third thing is the analyzer. So we have the analyzer here. Next thing is query. I'm going to take in the parser and actually parse the query. Parser.parse. And what am I looking at? I'm looking at my text, which is basically my search string. So let me just call it search string so that it makes it easier to understand. So I have the search string, and next thing is getting back the top docs, means the top hits for this particular search. So I have searcher.search q, which is my query parser, comma no, and I'm just restricting my results to 5. It doesn't matter, we're gonna have one result only. But again, when you do paging and all that stuff, it becomes important. You don't want to be returning all the results. So I'm going to say results found. And let's just call it top docs for now. Top docs.total hits. It's going to tell me how many hits were found, and then found these many documents matching the query. And I'm going to print the query too, so that you see what kind of format Lucene gets the query in. And then I'm going to iterate over matches. But when I do that, I need to create the list of string list, which was in the result class. So before I iterate this, I have my object ready. So when I do iterate over the top docs dot score docs, I can actually get back the document. And how do I get back the document? Searcher dot doc, and whatever the match is for that particular document, which is going to be in the score doc method, I get that value back, and then I'm going to add it to my collection. Once I do that, I'm going to say, okay, we matched. And don't worry if you don't understand this, because I'm going to go and repeat this once we're done writing this code. And then I have the field name. That sounds good. And all we need to do now is close the searcher once we've searched, and then return the result. Return new result. Result list equals matches and result. Oh, I don't have anything like result string. So probably, let me see. Oh yeah, I do. Now that is interesting. For some reason, it's not pulling that up. Result string equals to result. And that's pretty much it. So let me try to run this. So I do get an error. Well, because I think the class hasn't been completed. Still have an index error. Okay. Oh, sorry. That was going to be a comma. I think that was it. Now there's an ambiguous reference here between directory and Lucene, so I'm going to go ahead and create it Lucene. If I run this, I'm good. All right. So this code actually runs. Now what do we need? The next thing we need is actually the view. So if I now go to the view, there are certain things that I need to make this code run. So the first thing is I'm going to have input type equals to text, and then call it text search. Input type equals to submit. Value equals to search, and then go on click equals to search. I'm going to add a break here so that you can see what's going on. Then I have an ID, pre-result, style equals to display none. I don't want it to be shown beforehand, but I want it to be shown after some time. And this, all it says is string found, and maybe an ID for the actual result. So now the next thing is going and writing my JavaScript. I should technically get IntelliSense for this. So let's just build it and see, and that actually builds. So script type equals to text/JavaScript, and it should run. One other thing I might want to do is make sure that I have jQuery. So it does have jQuery. Okay, that's great. So the next thing would be to basically create this function, which is my search function. And use a $.ajax. Now why I like using this function is because it gives me the ability to describe what kind of function we're using. So if I have a get, I can actually say it's a get. Is going to be home search, and then I'm going to pass in the query string, which is going to be text equals. Actually, I could have done this the other way around, but it's okay. I'm going to say txt search dot val, and that should be it. So in case of success, I'll have another function saying just alert success. So once I have this, I can run it, except for one change that I probably need to make in here. And that should be it. Let's see what we get. So if I run this, and another thing that I forgot to add was this result string. So results found, one document matching the query string. Now we can get into a lot more details, but for hello world, it's kind of the longest hello world you've ever seen probably. So let's go and see what we actually did. So it's pretty simple. The first thing is that we chose a kind of a directory, which was a RAM directory. We could have used some other directories too, but we chose a RAM directory. We used an analyzer that took our data in. The data we're passing is this, which creates our document. Now this could have been a bigger text than what it is, but to make things simple. This code creates the document. I use the index writer to actually add that document to my index. Once I add the document, I commit it and then I close it. And this is a search piece where the reader opens up the connection, reads the index, reader, gives us that same exact data back. So when you search Chandar, you're going to get something. If you search something else, you're not going to get anything. Behind the scenes, creation of document was simple, just document.add. For searching, we're using query, parsing the query, whatever query it is. It parses into a syntax, which is easy for Lucene to understand. Now, all you're doing is really passing a string, and the query parser creates the real query for you. And then, after searching it, whatever documents you get back, you create a result that is easy to understand for your code. So in our case, we just created a class result and passed back the code. Now, what's the big deal about it? Since it was hello world, it's not that a big deal that, what did we really do in this application? We created an index. We really didn't have much big data, but we read that index and that's it. Let's look into the details why search becomes important, and we'll look into a real life example just in a bit. But before that, let's look into the PowerPoint again. So when we talk about the query, there are a few things that are involved. We construct the query, whatever the query is, and then we can filter on that query. We can sort on that query. Default sorting is by relevance. Now there are different kinds of queries that are available. The first one is a term query. You just pass in a term and it's going to search that particular term. And then there's prefix query. So we've all seen this wildcard. We start with something like LUCE and it's going to search everything that has Lucene and other documents in it. Then we have a range query, which can go from a numeric range to an alphanumeric range and also to a date range. Then there's something called Boolean query. This is very important. Whenever we search things, we want this result, but it should not contain something else. Things like that. Then we have phrase query. Well, we want to search these things, but we know that this is part of a phrase and I want to have a slop. Slop is more like a distance. So if there is a sentence that, we are going somewhere and you want to search for are and going, well, they're close to each other. That's fine. But maybe you want to search for are and somewhere and you know that the slop between them is 2 because they're just 2 words apart. Well, in this case, just 1 word apart. So you might want to give a slop. So that is something that could be searched. Now keep in mind the phrase queries are going to be slower than any other point queries. Then you have wild query. So wildcard query in this case, we've seen a prefix query is similar, but the difference is the prefix query means that it's starting from the beginning. In case of a wildcard, you can put it wherever you want to. So in this case, the question mark means that it could be any character. It could be 1, 2, H, like in this particular case, and it could be anything else, but it's got to be only one character. And a star really means any amount of characters. And then there's fuzzy queries. You want to do a pretty fuzzy query, which really is more like a phonetic search or something in a distance algorithm. What that really means is that, I'm trying to search something and I'm not really sure about it. So that is probably the slowest query out there, but it's got its own benefits. So default query parser syntax, you can see if you want to search a term query, Azure, you can search that. And then something like this. If you want to search Lucene and MVC4 internally inside Lucene, it'll become plus Lucene and plus MVC4. Lucene or Solar, you can search like that. Lucene.net, not Hadoop, is more like Lucene.net minus Hadoop. And then a field name like what we did. We had a field name and then it was called text colon Chandar, and that's how we searched it. Chandar becomes Chandar or anything like that, anything relevant like that. Again, we saw the wildcard query, and then we can also do middle initials from this to that. If you've done regular expressions, something similar is out there. And then we can create our own custom query parsers too. Two of the famous ones are right there. Then converting your text into terms is basically called the process of analysis. So Lucene does not search the text. Lucene really searches those terms, and creating those text into terms is analysis. Now you can have different kind of analyzers. You have simple analyzer, white space analyzer. Like the name suggests, it's going to remove the white spaces. There are simple analyzer might remove a, an, and the kind of keywords. You can create your own custom analyzers too. Then there's stems that'll take the plurals and make them singular. Obviously, the analyzers will remove the stop words, like I said, a, an, and the, and other kind of words that are redundant, that do not actually make a difference when we are looking for tokens. For example, the guy is a geek. When you remove the articles and it becomes guy geek. And then also add synonym filters. You're searching for color in US English and it's different in British English. So what do? Lucene takes care of that for you. This is probably one of the most important slides in the talk today. When we talk about fields can be indexed and they can be stored too. So when you index a field and you say, do not analyze it and have no norms, what that really means is that the field will be stored, but it's not going to have a term vector. Now examples are primary keys, phone numbers, URLs. You want to store them as it is. You don't want to remove anything from that. Dates, names, all these things that are very important to you and critical to your business, and they're small and they have to be the way they are. That's when you want to use an option like that. And then comes another one where it's analyzed as yes. Well, it's analyzed means it's going to be stored, great. But at the same time, it's also going to have a position and an offset. So think about a title or an abstract. Well, you want to really know where in your database is that particular title or that particular abstract, or in your file system. So let's say you're using something called MongoDB and we want to get back the title only for all your searches. And when you want to do that, you might want to use Lucene for that. Well, in that case, you can have the position and offset of wherever that title is coming from. Well, and that's the information that you're storing in your index, and you can make it work. Now, people have made Lucene work with Entity Framework, NHibernate, and all those things. I think NHibernate, it's also part of NHibernate now. And if you want to look into it, how they use it, it's pretty cool. And then there's another one where you can have it analyzed, but you may not want to store it. So the index is analyzed, but you haven't stored it. And the term vectors, positions plus offsets, one of the example. And there's another one where you have analyzed and you don't want to store it. Well, that's a good example of something big like a body, a whole text body of a web page. You don't want to store everything, but you want to have positions and offsets so that you can get back to the data you want. Another case is not analyzed. Well, that really means you have to store it because it's not really analyzed. Well, maybe not. In some cases, you may not want to store it and you may not actually want to analyze it either. Those are something like hidden keywords. So norms. We use norms for boosting. Whenever we want to boost certain words and phrases, even though they are not going to be coming up in the searches on a regular basis, if you do a normal search, we may not be able to see those words or those phrases, but we want to boost them up. We want the user to see them no matter what. So for example, the user is looking for a 27-inch monitor, and I really want to sell him a 24-inch monitor because I have a sale going on. Well, then that's the time when I can boost the sale up, because the moment the user sees a difference of $100 on that, he might be enticed to buy the 24-inch monitor. So that's where norms play a big part. They're used for boosting. They can increase the rank of certain words and phrases. Now, Lucene automatically ranks smaller words higher. So anytime you have smaller words, they're ranked higher just because they're smaller, easy to tokenize, and all that stuff. But you can always change that ranking. Term vector, we've seen so many times, I like this thing, but I want to find similar things. I really don't know what all they are. Well, that's when we use term vectors to find the similar data. They use the concept of inverted index with term frequency pairs. So how many times that things appears in that particular document. Using something like that, they're going to use an inverted index, and that makes similar documents searchable together. And it's got position and offset info for those terms, and it's used with phrase query and highlighters. And more like this. If you search for more like this inside Lucene, there's a whole different topic of how to find similar data. Let's do a real world demo where we can see all this and get into where we can use Lucene in real world. And I'm gonna what we're gonna do in this case is grab a piece of code from GitHub, and then search through that code and see if our tool actually makes sense. And it's a pretty cool tool that we can build in maybe 10 minutes. So let's go ahead and grab a GitHub project. So in this case, I'm gonna grab Bootstrap. I'll come in here and clone this project. So once this is done, I can see that I have Bootstrap in my data directory. And if I look at it, it's got like 259 files. So just do a cursory look at it. It's got a JavaScript file, and it's got some other scripts, which is okay, and that's good enough for us to make a search on. But in a way that we can actually search through that data. And that's kind of interesting. So the first thing that we would need to change in case of indexes, let's say this is where we're creating our indexes, is actually give them a directory. So maybe I want to remove all this code and say that my index directory is new directory info. That's where my index directory is. And then my data directory, well, sorry, that's my data directory, and my index directory is this. When I have both of these, I'll have the number of indexes right here, and I need the data directory, and that should be it. We actually got back. So I'm going to use the index directory here. Once I open that, I'm going to be using the index writer, which is going to be new index writer. It's going to take the directory. I'm going to pass in the analyzer. Same thing as what we did in the last project. Max field length limited, and that's it. Then when I index my directory, I'm going to create another function for that, which actually does index my whole directory no matter what it is. So anything inside the node directory will be indexed right here. So once I create this function, what do I need to do? First thing would be get all the directories inside that particular directory. So my data directory, which right now is data, get all the directories, and then I do a for each var directory in directories. this is going to be recursive. So I'm going to get into a directory, and then if it's another directory inside that directory, it should go through that same thing. Index writer, same directory, and we should be good. Now, once we are at the file level, what I want is loop through all the files inside that particular directory and get all those files, obviously. Once you get all those files, you loop through all these files and then index every single file with index writer. This is another function that we have to create. Now, if you're not following, doesn't matter. I'm going to go through this again when we complete this thing. This will be another function that I'm generating. All right. So in case of a file, if file really does not exist, so if it doesn't exist, well, in that case, just return. But if it does exist, then take a document. Document equals to new document. Then take text reader. Reader equals to new stream reader. So I'm going to start reading the file, whatever the path of the file is. And then I'm going to take the contents of that file and add that as a field. So if you see, it's again, the name is anything that we can save. For now, I'm going to call it contents. And the contents, I'm giving the reader. And then I'm adding that to the document. And then I'm also adding the field to the document. Another field. So see, last time we only used one field, which was text, but this time we're using two different fields. One is the contents and also the file name, because maybe at times all I need to know is the file name when I do a retrieval on something. Field.index.analyzed. Then I have index writer dot add document doc. That should. So again, we can use directory info to get us the directory, which is index directory, and equals to new directory info file path. So one dot open directory info. And that should be it. So that's a good one. It does not actually return a value because we never finished using this. So when we were here, we created the index directory and we kept going forward. What I need to know is, okay, how many index documents are getting back? It's going to be index writer dot max doc. And then I have index writer dot. Now you can use optimize if you want. This is going to be a one-time performance hit, but it makes it better for rest of the time. So you might want to use it not in real time, but if you're doing an overnight indexing, it's not a bad idea. And this is from the previous code we wrote, so I gotta go remove that. That should be. So before I run this, there are a couple of changes that I need to make in my code. One of the things you can see right here is that analyzer is here, but I'm not actually passing in the right analyzer. This is really taking the static analyzer which we did in the previous code. So just make a small change like this and we should be good to go. And then the text field, it was text in the previous code, but now that we have file name, I'm going to call it file name. And then we search on it. The relevance was 5. I'm just going to make it 50. Now this looks really good, and I'm going to run this. So when I run this, I'm going to just go ahead and type something like JS that exists in a string, and we can see like we got like 50 results, probably around 50 results. It's actually saying 121 documents match the query. File name has JS in it. It's pretty quick compared to anything else. So let's just go. So if I go back to my data directory and look for a string that makes sense, something like licensed. So we might want to search something like this inside. If I want to search license, that was part of the content. So I need to search the contents field. I'm going to go ahead and create contents and do a control F. This is reindexed by contents field. Now you don't have to do it every time, but for simplicity purposes, I'm showing you this. It says 68 documents matching the query contents, and it's taking you less than 50 milliseconds to search this. Best practices. Lucene is just not a DLL. There's a lot behind it. You have to know the concepts of information retrieval if you're working on search applications. Business cases drive a lot of decisions, so understanding the domain is the key. There are times when we get a lot of clients that have multiple languages, so different languages need to have different fields and indexes. They should not be combined with each other because that can get into a different mess. When we have multiple languages, we also should be using separate analyzers. Obviously, it makes sense to do that. Otherwise, we can have conflicting results. Wildcard queries can always slow things down, so because they're really searching on everything. We've already talked about removing this a, and the stop words. There are times when we might want to use bigrams to reduce the redundancy in search. But one thing to keep in mind is that they do not double the index size, they actually triple it. And when you are really creating those backgrounds, you need pretty much triple the memory to do it. We should always use synonym filters, but we got to keep in mind that it increases recall but lowers precision, and we've talked about that earlier in the talk. Well, if the analysis is complex, it slows the indexing process. The question that I get asked most of the times is, what do we do in that case? Well, the simple answer is depends on your business. Do you really need complex analysis? Can you do away with slower indexing? Now that might mean that you may not have a right intensive scenario, and that's where you're using indexing. And if it is something that can happen offline or at a time that your app is not being a lot, it does make sense to do complex analysis. If it's the other way around, that you really need near real-time results, well, in that case, maybe it's better to increase the performance on your indexes and speed up the process. Lucene in Action is one of the best books. I definitely recommend this book, and there are tons of resources online that you can follow. That's my email and that's my Twitter. I hope you like the talk. Please do give me your suggestions. Thanks.